Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another important topic. The topic is elastic waves. You know, in the last lectures, we have discussed the heat capacity of solids. We discussed Dulong-Pettit law. Then we discussed the Einstein model. We also discussed the drawbacks or shortcomings of Dulong-Pettit law and Einstein model of heat capacity of solids. As you know, we said at high temperatures, Einstein's model of heat capacity matches with the experimental observations, but at low temperatures, it fails to predict the experimental behavior of heat capacity of solids. Now, at low temperature, the behavior is explained by another model. That model is called Debye model. We have to discuss Debye model in coming lectures, but to understand the Debye model, we need to understand the idea of elastic waves, which is our today's topic. You know, the atoms in a crystal are not quite stationary, but they oscillate around their equilibrium positions as a result of thermal energy, and these oscillations are called lattice vibrations. Now, a solid is composed of discrete atoms, as you know, and we need to take into account this discreteness of lattice vibrations. However, you need to remember when the wavelength of the wave going through a solid is very long, we can disregard the atomic nature and treat the solid as a continuous medium. I repeat, let me write it. It is important when the wavelength of the wave going through a solid is very long, we can disregard the atomic nature and treat the solid as a continuous medium. And we call these waves through this continuous medium as elastic waves, right? Now, what we are going to do next, we are going to examine the propagation of an elastic wave in a sample of a solid in the shape of a long bar as shown in the figure. Let me draw the figure. So I have this. What is this? It is sample. Let me name it figure 1. Sample of a solid in the shape of a long bar, right? Now we want to address the problem of the propagation of a longitudinal wave through this sample, right? Propagation of a longitudinal wave through this sample. Remember, what is longitudinal wave? In the longitudinal wave, the medium particles vibrate in the same direction as that of the direction of the propagation of wave. You need to keep that in mind. Now, when this wave goes through this bar, this longitudinal wave, there will be displacement in the medium, and that displacement in the medium we represent by the function u of x. So what is u of x? It is elastic displacement at point x. So at different points, there will be different displacement in the medium. So u of x is representing the function of electric displacement as function of position x, right? Now we consider the portion of this bar. Let the coordinate at this point be x and this point be x plus dx. That means this distance between these two points is dx. We are considering a portion of the bar having length dx, right? Now, when wave goes through, this is the wave going through this bar. When the wave propagates through this bar, there will be strain in the bar, right? Now, how we define the strain? The strain is defined as, strain is defined as change in length per unit length, per unit length, change in length per unit length. So if E denotes strain, it will be du by dx, right? Where du is let me write it neatly. It is du by dx. Du is the change in length dx. So when wave goes through this bar, we are considering the portion dx. Over this length dx, there is change in length du. So strain is du by dx. So let me encircle it. We define strain this way. This is my equation first. We define another quantity which is related to strain, that's called stress. The stress S, as you know, is defined as the force per unit area, force per unit area. And this stress is also a function of x. That means when wave goes through this bar, there will be stress created at different positions. That stress will be different at different points along the length of the bar. So how we define, it is defined as force per unit area, and we know according to Hooke's law, the stress is proportional to the strain. So we write S is equal to YE. S is our stress and E is strain. The constant of proportionality Y is called Young's modulus of elasticity. Let me encircle it. S is YE and name it equation 2, where the elastic constant Y is known as Young's modulus. Young's modulus. Let me write it neatly. Now we are focusing on this portion of the bar having length dx as shown in the figure. Now we want to understand the dynamics of the bar, so we will use Newton's second law. So we can write for the motion let me write using Newton's second law of motion. We can write for the motion of the segment shown in the figure. Which segment? This segment, which has length dx. So let me write. I'll skip a page, no issue. For the motion of the segment shown in the figure, I can write let me use another color. I can write rho A prime dx times second order partial derivative of u with time equal to s at position x plus dx minus s at position x times a prime, where let me define my symbols, where rho is mass density of the bar, that's mass per unit volume. What is A prime? It is cross-sectional area of the bar, cross-sectional area of the bar. There is no additional symbol. So A prime is cross-sectional area. Now understand this equation. This is stress at position x plus dx. This is stress at position x. So when you multiply stress with the area of cross section, you get the force. So your right hand side is simply the net force on the element or segment. Let me write it is net force on the segment due to the propagation of wave, due to the propagation of the wave, right? What is our left hand side? It is simply mass times the acceleration. Second order derivative of displacement with time is acceleration. When you multiply density by area of cross section, you get what? When you first let me do it this way. When you multiply area with length of the segment, it will give you volume of the element. When you multiply volume by density, it is mass. It is simply mass of the element. Mass of the element. This one. And this is acceleration. So we have simply written for the element, mass times acceleration is net force on the element. Simple Newton's second law. So let us name this equation as equation 3. This was our first equation. So first we defined strain, then we defined stress, and we wrote Hooke's law. Stress is proportional to strain. Then we're writing now Newton's second law for this segment, right? So let us move forward. Writing S at x plus dx position minus S at position x equal to dou S by dou x times dx for a short segment. Our segment is short. See, here S is function of only x. So partial derivative and total derivative is one and the same thing. So if I write dou S by dou x times dx, it is just dou S, right? Which is this. So we write instead of this S at x plus dx minus S at x, we write dou S by dou x times dx, right? So when you do that, after that, what we have to do, or I should do it. What's my equation? My equation is rho A bar dx, right? Then I have second order derivative of u with time, partial derivative. Now in my right hand side, I'm writing dou S by dou x times dx, and I have this a bar here. See, this is my left hand side in equation third, rho a bar dx, then second order partial derivative of u with t. And in right hand side, I am replacing s at x plus dx minus s at x with this dou s by dou x times dx, and there is a bar in as a multiplier here, right? Then what we do, we substitute for s from equation 2. Substituting for s from equation 2. What is my equation 2? This is my equation 2. I replace s by ye. Let us do that. What will it become? My equation will become rho a bar dx times second order partial derivative of u with time. Then I will write instead of sye, so it will become dou by dou x of ye times, then I have dx a bar. This is ye I am writing instead of s, right? So you can see, let me use this color. This dx will go with this dx. This a bar will go with this a bar. So what remains then? Let me move to next page, or I will write here. What remains then? Rho second order partial derivative of u with t. This is my left hand side, rho times this derivative. On right hand side, I have dou by dou x of ye, right? What's our next step? Now using equation 1 for the strain, using equation 1 for the strain. What is our equation 1? Go to equation 1. Our equation 1 is E equaled du by dx. So we replace E by rho second order u derivative of u with t is y is constant. I write dou by dou x of, instead of E, I write du by dx. Now, what I get, when I adjust it, remember, as I said, u is only function of x, so its total derivative is same as partial derivative. So I can write it y just second order derivative of u with x, right? So what I get, After rearranging the things, I will get second order derivative of u with x minus rho by y times second order derivative of u with time. Let me write it, partial derivative is equal to 0. Check it. Second order derivative, you take this y in the left hand side will become rho by y. So you will get second order derivative of u with x minus rho by y times second order derivative of u with time. It will be 0, right? Let me name this equation. This is our equation 4, right? This was our 3. Now we have obtained our equation 4. This equation 4 is simply wave equation in one dimension, right? It has a solution. Its solution is in the form of a propagating plane wave. Its solution is in the form of a propagating plane wave, which we write as u equal to a e raised by iota times qx minus omega t. Let me name and circle this equation. Name it equation 5. What is it? U is equal to a e raised power iota times qx minus omega t, where q is the wave number and you know q is equal to 2 pi by lambda, lambda being the wavelength. And remember, some books write k symbol for wave number. So don't get confused. You need to define your symbols. So I am here denoting wave number with q, which is 2 pi by lambda. Lambda is the wavelength. And what is omega? Omega is the angular frequency, or sometimes we simply write omega is the frequency of the wave, right? And A is the amplitude of the wave. Maximum value of U is A, amplitude of the wave. So don't confuse this A with the A prime. We use it for area of cross section of the bar, right? So Q is wave number, which is 2 pi by lambda. Lambda is wavelength. Q is in some books written as K. A is amplitude of the wave. Omega is frequency or angular frequency of the wave. Now, when you substitute this solution in equation 4, so I write substitution of 5 in 4 leads to substitution of equation 5 in equation 4, that is the solution in 4 leads to omega is Vs times Q, where, let me name it, this is my equation 6, where Vs is square root of y by rho. This is my equation 7. But you need to check it at home. This is your homework. Check it. See what you have to check. You have u given by equation 5. You find its second order derivative with x, put it here. Then find its second order derivative with time, put it here in equation 4, and you will see it will satisfy equation 4 when omega is taken as Vs times Q, where Vs is square root of y by rho, right? Now, this equation 6, the relation given by equation 6, connecting the frequency and wave number is known as the dispersion relation. Right? Now, since the velocity of the wave is equal to omega by q, which you know from your wave theory course, it follows that Vs in equation 6 is equal to this velocity. So this Vs here is velocity of the wave, right? And you see from equation 7, the velocity of the wave is expressed in terms of the properties of the medium, Young's modulus of velocity and density, right? And you know, the wave under discussion is the familiar sound wave, right? Now I draw a figure. Omega versus Q. This is a straight line. I name it figure 2. This is the plot of dispersion relation for the elastic wave, which we are considering omega equal to Vs times Q. So such a plot is called dispersion curve for an elastic wave. So this figure shows dispersion relation for the elastic wave. As you can see, it's a straight line whose slope is equal to the velocity of the sound. Now this type of dispersion relation, where omega is related linearly, to Q, is satisfied by other familiar waves also. For example, an optical wave traveling in vacuum has a dispersion relation omega equal to CQ, where C is speed of light. Right? Sound waves in liquids and gases satisfy similar relations. Now, there are deviations also from this linear relationship. And those deviations are often observed, and that deviation is known as dispersion. I repeat, deviations from the linear relationship are often observed and this is known as dispersion. Now, you need to remember that we have treated a longitudinal wave here, but the same type of analysis also applies to a transverse wave. You know what's a transverse wave? In case of transverse wave, the displacement of the medium particles is perpendicular to the direction of propagation of the wave. So when we analyze transverse wave, which is also called a shear wave, that introduces a shear elastic constant analogous to Young's modulus, and the velocity of the shear wave is related to it by a similar equation to equation 7, this one, right? The two elastic constants can then be used to describe the propagation of an arbitrary elastic wave in the solid. But in this discussion, we are assuming that our solid is isotropic. Now, what is isotropic solid? You need to remember a solid material for which, let me write it, a solid material for which physical properties are independent of the orientation of the system. I repeat, a solid material for which physical properties are independent of the orientation of the system is called isotropic. This completes our lecture. I will summarize it before leaving it. So what we did today, we took a sample of a solid and considered the propagation of a longitudinal wave through it. We defined strain, we defined stress, then we wrote Newton's second law for the segment of the solid material, which was just mass times acceleration is called to net force. Then we wrote a solution for the wave equation obtained. We defined wave number, frequency, and I gave you the homework to check that equation 5 satisfies equation 4 when omega is equal to Vs times Q, where Vs is velocity of the wave, which is square root of y by rho. So we said this discussion is valid for isotropic solid, and the propagation of transverse wave can be similarly analyzed, but there will be one more elastic constant introduced into the equations. So this is all for today. Prepare your exams and do not forget to subscribe and like my channel. You can also leave comment in the comment box. Thank you. God bless you. Assalamu alaikum.